Hello there, and welcome to Life Beyond Seen, a place where curiosity slows its breathing, where science takes its shoes off at the door, and where complicated ideas are allowed to unfold gently, without urgency. This channel exists for moments like this one, when the world is loud enough already, and the mind wants something steady, something thoughtful, something that doesn't demand anything more than quiet attention. Tonight, we're going somewhere very far away without moving at all. Downward, not outward. Away from the stars, past the waves, below the reach of light, toward a place on Earth that remains stubbornly resistant to our best tools, our bravest explorers, and our most advanced machines. We're talking about the Mariana Trench. Not the ocean in general, not coral reefs or shipwrecks or the familiar blue surfaces we see in documentaries and postcards. This is about the deepest known point on the planet, a place so deep that Mount Everest, if dropped into it, would still be completely submerged, its peak buried beneath more than a mile of water. A place that exists beneath pressures so intense that they quietly erase the assumptions we make about exploration, technology, and human presence. A place we have technically reached, briefly, carefully, and rarely, but have never truly explored in any lasting or comfortable way. The trench sits there, unchanged by our satellites and unmoved by our maps. It does not respond to curiosity in the way mountains or deserts do. You cannot hike to it. You cannot circle it with aircraft. You cannot see it clearly from above. Its defining feature is not just depth, but separation. It is removed from the human scale in a way that feels almost deliberate. While space often captures our imagination as the ultimate unknown, the Mariana Trench exists right here on Earth, closer than the Moon, yet far less accessible. It does not feel dramatic or explosive. It feels quiet, heavy, patient. When people imagine deep ocean exploration, they often picture sleek submarines gliding smoothly through dark water, lights cutting clean paths through the black, cameras transmitting crisp images back to the surface. The reality is slower, riskier, and far less predictable. The trench does not offer forgiving conditions. It does not allow long stays. It does not tolerate mistakes. Everything that goes down there is under constant threat from forces that cannot be negotiated with or distracted. Pressure does not rush. It does not roar. It simply exists, unrelenting, waiting for weakness. And yet we keep trying. Not because it is practical, and not because it is profitable in the usual sense, but because the idea of a place remaining unexplored unsettles us. Humans have always been uncomfortable with blank spaces. We draw lines on maps, we assign names. We tell ourselves that once something has been visited, it has been understood. The Mariana Trench resists that impulse. A handful of brief descents do not translate into familiarity. Knowing where it is does not mean knowing what it contains, how it behaves, or what long-term exploration there would truly require. There is something quietly humbling about that. We live in an age where images from distant galaxies arrive daily on our screens, where autonomous robots roam the surface of Mars, and where global positioning systems can locate a phone within a few meters anywhere on Earth. Yet the deepest part of our own planet remains largely inaccessible, not because we haven't thought about it enough, but because the environment itself sets limits that technology still struggles to cross safely and repeatedly. As you listen to this, you might notice where you are. Maybe you're lying down. Maybe you're sitting somewhere familiar, a room you've been in countless times. Outside, the world is moving at its usual pace, or perhaps it has slowed for the night. Where are you listening from right now? Not in terms of coordinates or elevation, but in terms of atmosphere. Is it late? Is the light dim? Is the day finally letting go? It's interesting to think that while you're here, in a place designed for rest, there is another place on this planet where rest is not a concept that applies at all. Where nothing sleeps, because nothing experiences day or night. If you find this kind of slow exploration calming, if the idea of learning something without being rushed feels like a relief, then liking the video or subscribing is a simple way to help this space continue. It allows these quieter, longer journeys to reach people who might need them. There's no urgency attached to that, just something to keep in mind, the way you might notice a bookmark resting where you'll need it later. Now, when we talk about the Mariana Trench being impossible to explore, it's important to be precise about what that actually means. Humans have reached the bottom a small number of times, briefly, carefully. Those descents were not failures, they were remarkable achievements, but exploration is not just about touching a place once and leaving. True exploration involves repetition, observation over time, the ability to adjust, to linger, to return easily with better questions than you had before. By that definition, the trench remains mostly untouched. The reasons for this are not dramatic in the way disaster movies might suggest. There are no monstrous barriers or sudden walls. Instead, the obstacles are subtle, constant, and deeply physical. Pressure increases steadily with depth, and by the time you reach the bottom of the trench, it has reached levels that fundamentally change how materials behave. Metals compress, seals fail, electronics behave unpredictably. Even light itself becomes irrelevant, absorbed long before it can reach those depths. What remains is a world governed almost entirely by forces we rarely experience directly. The ocean above the trench is not empty either. It is layered, dynamic, and in motion. Currents shift, temperatures drop, chemical compositions change. Everything that descends must pass through these layers, each one presenting its own challenges. Communication becomes delayed, distorted, or lost entirely. Navigation relies on sound rather than sight. Every signal sent down takes time to return, if it returns at all. There is no real-time control in the way we're accustomed to. Exploration becomes an exercise in patience and trust. And then there is the simple issue of distance. The trench is not just deep, it is remote. Located in the western Pacific Ocean, it lies far from major ports, far from rapid rescue capabilities, far from the infrastructure that supports repeated missions. Every expedition requires months of planning, enormous cost, and a narrow margin for error. This alone limits how often exploration can occur and how experimental or flexible it can be. But perhaps the most important reason the Mariana Trench remains so difficult to explore is that it does not behave like the environments we evolved to understand. On land, gravity dominates. In shallow water, buoyancy offers balance. In deep space, microgravity changes the rules entirely. In the trench, pressure becomes the defining factor. It does not allow improvisation. It does not allow exposure. Everything must be built specifically for it, tested repeatedly, and accepted with the understanding that failure is not dramatic but absolute. This creates a strange paradox. The trench is not hostile in the way a storm is hostile. It does not actively attack. It simply exists in a state that makes most human tools unsuitable by default. Life exists there, adapted over millions of years to conditions that would destroy unprotected human equipment in seconds. Fish with bodies that compress without harm. Microorganisms that thrive in chemical environments that would corrode machinery. Existence continues quietly, without awareness of how unreachable it seems to us. As we move forward from here, the focus will not be on spectacle. There are no sudden reveals waiting at the bottom. What makes the Mariana Trench compelling is not what we imagine it hides, but what it reveals about limits. Limits of engineering, limits of materials, limits of human presence. It is a reminder that exploration is not just about curiosity, but about compatibility. Some environments simply do not align with our bodies or our tools, no matter how determined we are. From here, we'll begin to unpack this slowly, not by jumping straight to the bottom, but by understanding the scale involved, the physical reality of depth, and why vertical distance underwater is different from almost any other kind of distance we encounter. The descent matters, the layers matter. And before anything reaches the trench floor, it has already passed through conditions that quietly reshape what exploration means. So settle in. There's no rush downward. The ocean is very patient, and it has been waiting far longer than we have. When people hear the phrase "the deepest place on Earth," it often sounds like a superlative meant to impress rather than a description of a real location. Deepest feels abstract, almost symbolic, like tallest mountain or longest river. But the Mariana Trench is not an idea or a metaphor. It is a physical place with coordinates, contours and boundaries, carved slowly into the planet by geological forces that do not pause to consider whether humans are ready to understand them. And despite being mapped, named and briefly visited, it continues to elude us in ways that are easy to underestimate. The trench lies in the western Pacific Ocean, east of the Philippines, stretching for more than 2,500 kilometers. It is not a single pit or hole, but a long crescent-shaped scar in the Earth's crust formed where the Pacific Plate slides beneath the smaller Mariana Plate. This process, known as subduction, happens extremely slowly, measured in centimeters per year, yet over millions of years it has created a feature so deep that it redefines what depth means. At its lowest known point, called Challenger Deep, the seafloor sits nearly 11,000 meters below the ocean's surface. Numbers like that tend to lose meaning quickly. 11,000 meters is hard to picture because it exists outside everyday experience. One way to ground it is comparison. If you placed Mount Everest at the bottom of the trench, its summit would still be buried under more than a kilometre of water. Commercial airplanes fly at altitudes that are less than half the depth of Challenger Deep. The trench is deeper than the highest point on land is tall, and that imbalance alone hints at why it remains so difficult to explore. Our intuition, shaped by life on land, simply isn't built for this kind of vertical scale. What makes the Mariana Trench particularly elusive is not just its depth, but the fact that depth in the ocean behaves differently than height on land. Climbing a mountain exposes you gradually to thinner air, colder temperatures, and reduced oxygen, but the pressure decreases as you go up. In the ocean, pressure does the opposite. Every metre downward adds more weight from the water above. By the time you reach the bottom of the trench, the pressure is more than 1,000 times greater than atmospheric pressure at sea level. That means every square centimetre of surface is being squeezed by a force equivalent to a small car. This pressure does not fluctuate dramatically. It does not surge or retreat. It is constant, uniform and unforgiving. Materials that seem rigid and strong on land behave very differently under those conditions. Steel compresses, glass shatters, even tiny imperfections in seals or joints can become catastrophic points of failure. Unlike surface exploration, where a broken component can sometimes be repaired or worked around, deep-sea exploration allows no margin for improvisation. If something fails, it fails completely. Yet humans have reached the bottom. This fact is often cited as proof that the trench has been conquered, or at least accessed. In reality, those descents underscore how limited our reach still is. The first successful crewed descent happened in 1960, when Jacques Piccard and Don Walsh reached Challenger Deep aboard the bathyscaphe Trieste. They spent about 20 minutes on the seafloor before ascending. The second crewed descent did not occur until 2012, when filmmaker James Cameron made a solo dive in the Deep-Sea Challenger submersible. A handful of uncrewed vehicles have followed, but each mission remains rare, expensive and brief. These descents are not exploration in the sense that we usually mean it. They're closer to controlled visits, a short arrival, limited observation through small viewports or cameras, minimal movement and a careful departure. There is no wandering, no extended surveying, no staying to see how conditions change over time. The trench does not allow lingering, and that alone separates it from most other places humans have explored. Another reason the trench remains elusive is that it is not visually accessible in any meaningful way. On land, exploration relies heavily on sight. We photograph landscapes, scan horizons, and use visual landmarks to orient ourselves. In the deep ocean, light disappears quickly. Sunlight barely penetrates the first few hundred meters. By the time you reach a depth of 1,000 meters, it is effectively pitch black. At 11,000 meters, darkness is total. Any visibility depends entirely on artificial light, which itself is limited by power constraints and the way light scatters in water. Artificial lighting creates its own problems. Bright lights illuminate only a small area surrounded by blackness. Sediment stirred up by movement reflects light back toward the camera, creating a kind of underwater fog. Shadows behave differently, depth perception becomes unreliable, and the field of view is narrow. Even high-definition cameras struggle to provide context. You can see an object, but not how large it is, how far away it lies, or how it fits into the surrounding terrain. Sound travels better in water than light, which is why sonar is used to map the seafloor. But sonar mapping, especially at extreme depths, comes with limitations. High-resolution mapping requires proximity, which increases risk. Long-range sonar provides broader outlines but lacks fine detail. As a result, our maps of the trench are still approximations. We know its general shape, but many features remain unresolved, smoothed over by data gaps and technical constraints. There is also the issue of time. Getting to the bottom of the trench takes hours. Descending slowly is essential to avoid stressing equipment and to manage buoyancy changes. Once there, battery life limits how long instruments can operate. Every minute spent at depth is borrowed time, balanced against the need to return safely to the surface. This means that even the most advanced missions collect only small snapshots of data. They do not capture processes that unfold over days, weeks, or years, and processes do unfold there. Despite its isolation, the trench is not static. Sediment slides occur, chemical gradients shift, organic material drifts down from the surface, providing food for organisms adapted to extreme pressure. Tectonic activity continues silently, reshaping the seafloor on timescales we rarely witness directly. Understanding these dynamics would require sustained observation, something we simply cannot yet maintain at such depths. The remoteness of the trench adds another layer of difficulty. Unlike space missions, which benefit from global networks of tracking stations and decades of infrastructure development, deep-sea exploration operates with limited support. Launching an expedition to the Mariana Trench requires specialized ships, crews trained for extreme conditions, and equipment that often has no backup. Weather conditions on the surface can delay or cancel missions, even when everything below is calm. There is no easy way to recover a lost vehicle or repair damaged equipment once it has descended. Cost plays a role as well. Building submersibles capable of withstanding trench pressures is extraordinarily expensive. Testing them is equally demanding, requiring pressure chambers that can simulate conditions found nowhere else on Earth. Every mission represents a significant financial risk, and failure can mean the permanent loss of equipment worth millions. This reality limits how experimental or ambitious missions can be. Exploration becomes cautious by necessity. Perhaps the most subtle reason the trench eludes us is psychological. Humans are drawn to environments where presence feels possible. Even in space, astronauts can float, move, and interact with their surroundings in a way that resembles freedom. In the trench, there is no such sense. Movement is constrained. The environment does not respond. There is no horizon, no sky, no variation in light. Everything feels compressed, enclosed, and final. It is an environment that resists human intuition, making it harder to design missions that feel exploratory rather than purely observational. And yet, the trench continues to matter. It matters scientifically because it represents an extreme that tests our understanding of geology, biology, and physics. It matters philosophically because it challenges the assumption that everything on Earth is within our reach. It reminds us that familiarity with the surface does not translate into mastery of the whole planet. Most of Earth's volume is ocean, and most of that ocean is deep. The Mariana Trench is simply the most dramatic example of a broader truth. What we know about the trench has been pieced together slowly, from fragments of data collected under difficult conditions. Each mission adds a little more clarity, but also reveals how much remains unknown. We have images of the sea floor, samples of sediment, recordings of sounds, and glimpses of life adapted to crushing pressure. But these are pieces, not a complete picture. The trench remains a place we visit rather than inhabit, observe rather than understand. As we continue, the question is not just why the Mariana Trench is deep, but why depth itself changes everything. Why moving downward through water is fundamentally different from moving upward through air. Why pressure, darkness, and isolation combine to create an environment that resists long-term human presence. Before we can appreciate the specific challenges of machinery, biology, and communication, it helps to understand the sheer scale involved and how the ocean transforms distance into something far more demanding than it first appears. When we talk about the Mariana Trench, it is tempting to imagine it as a destination at the bottom of the sea, a final point you reach after a long descent, much like arriving at the base of a canyon. But that way of thinking misses something fundamental. The trench is not simply a bottom. It is a vertical world, an entire ocean stacked layer upon layer, each with its own conditions, behaviours and boundaries, stretching downward far beyond what human intuition is comfortable with. To understand why this place remains so difficult to explore, it helps to stop thinking horizontally and start thinking vertically. On land, distance is usually measured across a surface. We travel kilometres along roads, across plains, over hills. Even when we think about mountains, height is treated as a challenge layered on top of horizontal movement. You climb up while still existing within a familiar world of air, gravity, and visibility. In the ocean, depth replaces distance. Movement is not across terrain but through it. You do not walk over the environment, you sink into it, and the deeper you go, the more the environment itself changes. The Mariana Trench exists at the far end of this vertical transformation, but between the surface and the bottom lies nearly 11 kilometres of water, and that water is not uniform. It is divided into zones that differ in temperature, pressure, chemistry, light, and life. Each zone presents its own challenges, and none of them can be skipped. Anything sent to the trench must survive every layer on the way down and on the way back up. At the surface, the ocean feels familiar. Sunlight penetrates easily. Waves move energy through water. Temperatures fluctuate with weather and seasons. Ships float. Humans can swim, dive briefly, and return without special equipment. This is the epipelagic zone, extending down roughly 200 metres. It represents a thin skin compared to the full depth of the ocean, yet it is where most human interaction with the sea occurs. Below this lies the mesopelagic zone, sometimes called the twilight zone. Light fades rapidly here. Colours disappear. Red wavelengths vanish first, followed by others, until everything takes on shades of blue and grey. By 1,000 metres, sunlight is essentially gone. Temperatures drop. Pressure increases to levels that already require specialised equipment. Many organisms here produce their own light, using bioluminescence to communicate, hunt, or hide. This zone alone is deeper than most lakes along. Descending further brings you into the bathypelagic zone. This is where the ocean begins to feel truly alien. Temperatures hover just above freezing. Pressure continues to rise steadily. There is no natural light at all. Life exists, but it is sparse, slow-moving, and highly specialised. Energy is limited. Food arrives mostly as a slow rain of organic matter drifting down from above. This vertical distance from the surface to here already exceeds the depth most submarines can safely reach. Below that lies the abyssopelagic zone, stretching down to about 6,000 metres. This is the abyssal plain region, a vast, cold, dark expanse that covers much of the ocean floor. The pressure here is hundreds of times greater than at the surface. Temperatures remain near freezing. The seafloor is often covered in fine sediment, accumulated over millions of years. Exploration at these depths is rare but not unheard of. Robotic vehicles can operate here for limited periods. Humans, however, cannot. And then, finally, below the abyss, the Hadal Zone begins. This is the realm of deep ocean trenches, including the Mariana Trench. The Hadal Zone exists only in certain parts of the world, where tectonic forces have pulled the crust downward into narrow, steep-sided depressions. These trenches are not wide plains. They are confined, steep, and complex, with slopes that can collapse and reshape over time. The Mariana Trench's vertical scale becomes particularly difficult to grasp here. From the edge of the trench to the bottom, the drop can be several kilometres. The walls are not smooth, they're fractured, layered and unstable. Sediment slides downward, rocks shift. The shape of the trench floor can change subtly over time, making mapping difficult and navigation uncertain. Pressure at the bottom of Challenger Deep exceeds 1,100 atmospheres. That number is often repeated, but its implications deserve attention. Pressure increases linearly with depth, meaning that every additional metre adds weight. There is no point at which the pressure levels off or becomes manageable. It simply keeps building. By the time you reach the bottom, the force exerted on every exposed surface is immense and constant. This pressure does not just threaten large structures, it affects small components in ways that are difficult to predict. Seals that function perfectly at shallower depths may fail. Electronics may behave erratically. Materials that are slightly porous at the microscopic level can allow water intrusion under pressure. Even lubricants can compress or change viscosity, affecting moving parts. The vertical distance also complicates communication. Radio waves do not travel well through water, especially at depth. Instead, communication relies on sound, which moves slowly compared to electromagnetic signals. Commands sent from the surface to a deep vehicle can take seconds to arrive. Responses take just as long to return. This delay makes real-time control impossible. Operators must anticipate conditions and trust autonomous systems to handle unexpected situations. Navigation presents another challenge. GPS signals do not penetrate water. Deep-sea vehicles must rely on inertial navigation systems, acoustic beacons, or pre-mapped reference points. In a trench environment, where walls are steep and features are irregular, maintaining precise location awareness is difficult. A small navigational error can mean drifting into a slope or losing orientation entirely. Time behaves differently in a vertical ocean as well. Descent is slow by necessity. Rapid changes in pressure can damage equipment or destabilize buoyancy. Vehicles must adjust gradually, compensating for compression of materials and changes in water density. Ascending requires the same care. As a result, a single mission to the trench can take many hours just to reach the bottom and return, leaving limited time for actual observation. Energy becomes a limiting factor. Batteries must power lights, cameras, sensors, propulsion, and communication systems. At extreme depths, cold temperatures reduce battery efficiency. Pressure-resistant housings add weight. Every additional instrument increases energy demand. Designers must make careful trade-offs, deciding what data is worth collecting and what must be left out. The vertical scale also affects human perception of risk. On land, danger often feels visible. You can see a cliff edge. You can judge weather conditions. In the deep ocean, threats are invisible and omnipresent. Pressure cannot be seen. Darkness is total. There is no external reference point to provide reassurance. This makes human presence psychologically challenging, even in highly controlled environments. When humans have descended to the bottom of the Mariana Trench, they have done so in vehicles designed as pressure vessels, essentially small, sealed capsules surrounded by thick walls. The occupants do not experience the pressure directly, but they are constantly aware of it. Every sound, every vibration carries weight. There is no escape route, no emergency ascent. Safety depends entirely on the integrity of the vessel. The trench's vertical nature also limits rescue possibilities. In most forms of exploration, redundancy is built into planning. If something goes wrong, help can arrive. In the Hadal zone, there is no quick rescue. Another vehicle cannot simply descend to assist. The time, cost, and risk involved make rescue operations largely theoretical. This reality shapes mission planning and limits the willingness to take risks. From a scientific perspective, the vertical structure of the ocean complicates interpretation of data. Conditions change continuously with depth. A measurement taken at one level may not apply even a few hundred meters below. To understand processes occurring at the bottom, scientists must consider everything happening above it. Chemical gradients, particle flux, and biological interactions all depend on vertical movement through the water column. Even life itself reflects this vertical organization. Species found in the trench are not simply deep water versions of surface organisms. They are adapted to specific pressure ranges and chemical conditions. Many cannot survive outside their narrow depth band. This means that collecting samples without damaging them is extremely difficult. Bringing organisms to the surface often alters or destroys them, limiting what can be learned. The sheer scale of the vertical ocean also affects how we think about mapping and ownership. On land, borders and boundaries are drawn on surfaces. In the ocean, especially in trenches, depth adds complexity. International waters may extend downward, but jurisdiction over resources and research becomes murky. The trench exists far below any practical enforcement or governance, adding another layer of inaccessibility. Understanding the Mariana Trench, then, is not just about reaching the bottom. It is about comprehending the immense vertical journey required to get there. Each layer demands different solutions. Each meter adds pressure, removes light, and narrows options. The ocean does not present itself as a single environment, but as a stacked series of worlds, each more demanding than the last. As we continue deeper into this discussion, it becomes clear that the challenges of exploring the trench are not isolated problems. They are cumulative. Pressure, darkness, distance, time, and energy all build on one another, reinforcing the difficulty. The trench is not protected by a single barrier, but by the combined weight of the entire ocean above it. This vertical perspective helps explain why progress has been slow and why exploration remains limited. It is not a lack of curiosity or ambition. It is the reality that descending through nearly 11 kilometers of hostile shifting conditions requires patience, precision, and technology that is still being refined. And before we even consider what waits at the bottom, we must understand what the ocean itself becomes as it stretches downward, transforming from something familiar into something almost entirely other. Water is usually associated with softness. It flows around obstacles, fills empty spaces, yields to movement. We drink it, wash with it, swim through it. Even when it becomes rough, forming waves or storms, we still think of it as something that moves rather than something that presses. But in the depths of the ocean, water stops behaving like a gentle substance and begins to act like a weight. Not metaphorically, not symbolically, but physically, relentlessly, and without pause. In the Mariana Trench, water is no longer just a medium you move through. It becomes the dominant force shaping everything that exists there. Pressure is the defining condition of the trench. More than darkness, more than cold, more than isolation, it is pressure that turns the deep ocean into a place fundamentally incompatible with ordinary exploration. Pressure is not dramatic in the way explosions or storms are dramatic. It does not announce itself. It does not fluctuate wildly. It simply increases, steadily and predictably, as depth increases. And by the time you reach the bottom of the Mariana Trench, That steady increase has accumulated into something almost incomprehensible. At sea level, the air around us presses down with a force of about 1 atmosphere, roughly 101 kilopascals. Our bodies are adapted to this. We do not feel it because the pressure inside our bodies balances the pressure outside. The moment you step into water, that balance begins to change. Water is much denser than air, and even a few meters below the surface, pressure starts to increase noticeably. Divers feel it in their ears. At 10 meters, pressure has doubled. At 30 meters, it has quadrupled. These are depths that recreational divers approach cautiously, with training and strict limits. Now imagine extending that same principle downward, not for tens of meters, but for thousands. Pressure increases by about 1 atmosphere for every 10 meters of depth. This means that at 1,000 meters, pressure is around 100 atmospheres. At 10,000 meters, it exceeds 1,000 atmospheres. At Challenger Deep, the pressure is roughly 100 times what we experience at the surface. Every square centimetre is under a force equivalent to more than a metric ton. This pressure is uniform. It comes from all directions. There is no side that is spared, no orientation that offers relief. Unlike gravity, which pulls downward, pressure squeezes inward. It presses equally on top, bottom and sides. This is why pressure vessels used in deep-sea exploration are typically spherical or cylindrical with rounded ends. Sharp corners concentrate stress. Flat surfaces bow inward. Under trench-level pressure, even small design flaws are magnified. For a human body, this pressure is instantly fatal without protection. Our bodies contain air-filled spaces, like lungs and sinuses, that cannot withstand compression beyond certain limits. Even before reaching extreme depths, nitrogen dissolves into the bloodstream under pressure, creating risks that divers must manage carefully. At trench depths, unprotected human tissue would not simply be injured, it would be crushed. The distinction matters because it highlights how absolute the barrier is. This is not a place where humans can adapt through training alone. But pressure does not only threaten living organisms, it challenges materials in ways that are difficult to fully predict. Metals compress, plastics become brittle, glass fractures. Even materials designed for strength behave differently under constant multi-directional stress. A material that performs perfectly in laboratory conditions may fail unexpectedly after hours under extreme pressure, not because it is weak, but because microscopic imperfections become points of failure. Seals are particularly vulnerable. O-rings, gaskets, and joints that keep water out of electronic housings must perform flawlessly. At depth, water is forced into any available space. Even gaps smaller than a human hair can allow intrusion. Once water enters an electronic system under pressure, it does not seep gently. It is driven inward with force, short-circuiting components and rendering systems useless almost instantly. Pressure also affects fluids inside machinery. Lubricants compress, their viscosity changes. Moving parts that rely on precise tolerances may seize or behave erratically. Hydraulic systems must be designed to operate under external pressures far greater than those they generate internally. This adds complexity, weight, and cost to every component. Even buoyancy, a principle that seems straightforward near the surface, becomes complicated at extreme depths. Buoyant materials compress under pressure, losing volume and lift. Foam that provides buoyancy at shallow depths may become ineffective as it is squeezed smaller and smaller. Designers must account for this compression, often using specialized syntactic foams made of microscopic hollow spheres embedded in resin. These materials are expensive, difficult to manufacture, and still have depth limits. Pressure also imposes constraints on shape and size. Large structures are harder to protect than small ones. The thicker the walls of a pressure vessel, the heavier it becomes. Increased weight requires more buoyancy, or more powerful propulsion, which in turn demands more energy. This creates a cascade of trade-offs. Making something strong enough to survive the pressure makes it heavier, which makes it harder to move and control. Then there is the issue of fatigue. Materials under constant stress behave differently over time. Even if a structure survives initial exposure to pressure, repeated cycles of descent and ascent can weaken it. Microfractures can develop, seals can degrade, components that passed initial testing may fail after several missions. This limits how often vehicles can be reused and increases the need for thorough inspection and refurbishment. Pressure also complicates data collection itself. Sensors must be calibrated to function accurately under compression. Instruments designed to measure chemical concentrations, temperature or movement must maintain precision despite being physically squeezed. Even slight deformation can affect readings. This means that interpreting data from the trench requires careful consideration of how pressure may have influenced the instruments themselves. The crushing force of water also shapes the environment of the trench. Sediment behaves differently under pressure. Fine particles settle slowly from above, forming thick layers on the seafloor. Landslides can occur along the trench walls, triggered by earthquakes or gradual destabilization. These movements can reshape the bottom, burying features and altering habitats. Mapping efforts must account for the possibility that the terrain itself is not static. Life in the trench exists because it has adapted to this pressure, not despite it. The organisms found there do not resist pressure, they accommodate it. Their bodies lack air-filled spaces. Their cell membranes and proteins are structured to function under compression. Enzymes that would denature at high pressure in surface organisms remain stable. These adaptations are not minor tweaks, they are fundamental differences at the molecular level. However, studying these organisms is exceptionally difficult precisely because of pressure. Bringing samples to the surface often destroys them. As pressure decreases, cellular structures fail, gases expand, tissues rupture. To study trench life properly, scientists must either observe organisms in situ or develop pressure-maintaining containers that can preserve conditions during ascent. Such systems exist, but they are limited, complex, and rarely used at the deepest depths. Pressure also affects sound propagation. While sound travels well in water, extreme pressure and temperature gradients can bend sound waves, creating shadow zones and distortions. This complicates acoustic communication and mapping. Signals sent from the surface may arrive weakened or altered. Reflections from the seafloor can be difficult to interpret, especially in a confined trench environment. For crewed missions, pressure is a constant psychological presence. Even though the occupants are shielded inside a pressure vessel, they are aware that the outside environment is exerting enormous force on the hull. Every creak, every unexpected sound becomes meaningful. There is no redundancy in the way there is redundancy in aircraft or spacecraft. The hull is the barrier, its integrity is everything. This awareness shapes mission duration. Staying longer does not reduce risk, it increases it. The longer a vehicle remains under pressure, the more opportunity there is for something to go wrong. Heat buildup, material fatigue, power drain, and unforeseen interactions all become more likely with time. As a result, missions to the trench are designed to be as brief as possible. Pressure also limits innovation. New designs cannot be tested easily at full depth. Pressure chambers capable of simulating trench conditions are rare and expensive. Even then, they cannot perfectly replicate the combined effects of pressure, cold, and time. This means that some failures only reveal themselves during actual missions, when recovery may not be possible. Compared to space exploration, where vacuum and radiation present their own challenges, deep-sea exploration faces a different kind of hostility. Space pushes outward, the trench pushes inward. In space, structures must contain internal pressure against an external void. In the trench, they must resist external pressure crushing inward. The engineering problems are not mirror images. They require different materials, different safety margins, and different philosophies. The crushing force of water also reshapes how we think about presence. On land, exploration often involves movement through space. In the trench, presence is static. Vehicles descend, hover, observe, and leave. There is no walking, no standing, no physical interaction beyond what robotic arms can manage. Pressure makes physical contact with the environment risky. Touching the seafloor can stir sediment that obscures visibility. Contact with the trench walls can damage equipment. Pressure also enforces isolation. Cables connecting vehicles to the surface are impractical at these depths. They would need to be incredibly strong, heavy, and resistant to abrasion. Most trench missions rely on untethered vehicles, which means that once they descend, they're effectively alone. Communication is limited. Control is indirect. Recovery depends on the vehicle's ability to return on its own. This isolation reinforces the sense that the trench is not just deep, but separated. It is not merely far away. It exists under conditions that make sustained interaction nearly impossible. Pressure is the reason for this separation. It is the invisible wall that surrounds the trench, not as a boundary you cross once, but as a force you endure continuously. Understanding pressure is essential to understanding why the Mariana Trench remains so resistant to exploration. It is not that we lack the desire to go there. It is that every additional meter downward increases the demands placed on our tools, our planning, and our tolerance for risk. Pressure turns water into a crushing force that never rests, never negotiates, and never relents. As we continue, this pressure will remain a constant background presence, influencing every other challenge we encounter. Darkness becomes more absolute under pressure. Cold becomes more penetrating. Distance becomes more costly. Even the simplest tasks, like turning on a light or moving forward a few meters, are shaped by the force pressing in from all sides. And once pressure has set the rules, everything else must follow. Light is one of the quiet assumptions built into almost everything humans do. We design tools expecting visibility. We navigate by sight. We describe environments using color, shape, contrast, and distance, all concepts rooted in the presence of light. Even danger often announces itself visually. A steep drop, a storm cloud, a moving object. Darkness, on land, is usually temporary. Night passes. Artificial lights can push it back. In the depths of the Mariana Trench, darkness is not an absence waiting to be filled. It is a permanent condition, absolute, uninterrupted, and indifferent to effort. Sunlight does not slowly fade as you descend toward the trench. It disappears decisively. The ocean absorbs light efficiently, and different wavelengths vanish at different depths. Reds go first, then oranges, yellows, and greens. By the time you reach a few hundred meters, the world is already stripped of colour. Objects appear blue or grey, if they appear at all. Below roughly 1,000 meters, sunlight is gone entirely. Not dim, not twilight. Gone. The trench exists thousands of meters below that point, in a darkness that has persisted for millions of years. This kind of darkness is difficult to conceptualize because it has no reference point. On land, even in a cave or a sealed room, there is usually some ambient glow, some sense of space defined by faint contrast. In the deep ocean, without artificial light, there is nothing. No up or down, no near or far. Space collapses into a uniform blackness that offers no information. For exploration, this is not just inconvenient, it is transformative. Exploration relies on awareness. You need to know where you are, what surrounds you, and how those surroundings change as you move. Darkness strips away passive awareness. Without light, there is no peripheral vision. Nothing enters your field of view unless you actively illuminate it. This means that exploration becomes reactive rather than observational. You do not notice something and then decide how to respond. You decide where to shine light and only then learn what exists there. Artificial lighting is the obvious solution, but it introduces its own problems. Light sources require power, and power is limited. High-intensity lights drain batteries quickly, reducing mission duration. They also generate heat, which must be managed carefully in an environment where heat dissipation behaves differently. Too much heat can damage equipment or alter the surrounding water chemistry in subtle ways. Light in water does not behave like light in air. Water scatters light, especially when particles are present. The seafloor of the trench is covered in fine sediment that is easily disturbed. When a vehicle approaches or lands, it stirs up this sediment, creating clouds that reflect light back toward the camera. The result is a blinding effect, where illuminated particles dominate the image and obscure everything beyond them. This is not fog that slowly clears. In the still water of the trench, sediment can remain suspended for long periods. This scattering severely limits visibility. Even with powerful lights, the effective viewing distance is often only a few meters. Beyond that, darkness swallows detail. Large features may exist just outside the illuminated cone, but they remain invisible. This makes navigation difficult and mapping incomplete. You may see a small patch of seafloor in high detail, while having no sense of the broader terrain. Shadows behave differently as well. In an environment with a single localized light source, shadows are sharp and absolute. There is no ambient light to soften edges. Objects can appear and disappear abruptly as the angle of illumination changes. A rock can look like a wall. A slope can appear flat. Depth perception becomes unreliable, especially when the camera lacks reference points for scale. For human occupants of submersibles, this visual isolation can be disorienting. The view through a viewport or on a screen is narrow. Everything outside that view effectively does not exist. There is no horizon to anchor perspective, no sky to provide orientation. The environment does not offer cues that humans evolved to rely on. Even experienced pilots must consciously manage their sense of space and movement. Darkness also complicates scientific observation. Many geological features are identified visually through patterns, textures, and spatial relationships. In the trench, these must be inferred from limited visual data combined with sonar and other instruments. This indirect understanding increases uncertainty. You may detect an anomaly acoustically, but lack the visual context to interpret it confidently. Biological observation is even more affected. Many trench organisms are small, transparent, or slow-moving. They may not reflect light strongly. Some actively avoid illumination, retreating into sediment or out of view. Others produce their own light, but bioluminescence is often brief and subtle. Capturing these moments requires patience, luck, and careful positioning, all under severe time and energy constraints. Darkness also alters behavior. For organisms adapted to the trench, light is not a neutral presence. It can be disruptive. Sudden illumination may trigger stress responses, flight, or defensive behaviors. This means that observing life under artificial light may change what you're trying to study. The act of seeing becomes an intervention. From a technological standpoint, darkness removes the possibility of passive monitoring. Cameras must be active. Sensors must compensate. Data must be interpreted with the understanding that what is unseen may be just as important as what is visible. This creates blind spots that are difficult to quantify. You do not know what you are missing because you cannot see the boundaries of your ignorance. Navigation suffers as well. On land or in shallow water, visual landmarks help maintain orientation. In the trench, navigation relies heavily on instruments. Inertial navigation systems track movement over time, but small errors accumulate. Acoustic positioning systems require beacons or reference points that are difficult to deploy and maintain at depth. Darkness removes a layer of redundancy. There is no visual confirmation to correct instrument drift. Even simple tasks like manipulating objects with robotic arms become complex. Depth perception is limited. Shadows obscure edges. Fine movements are difficult to judge. Touch becomes risky, as contact can stir sediment or damage fragile structures. Operators must rely on experience and careful control, knowing that mistakes are harder to see before they happen. The psychological impact of absolute darkness should not be underestimated. Humans are not comfortable without visual input. Sight provides reassurance, even when it reveals danger. Darkness offers no such comfort. It amplifies uncertainty. In the trench, darkness is not something you can look past or wait out. It is total and persistent. This persistence affects mission planning. There is no advantage to timing a descent for daylight. There is no change in conditions between hours or seasons. The trench is always dark. This removes one variable, but reinforces the sense of isolation. Time loses some of its usual meaning. Without external cues, hours blend together. Attention must be maintained deliberately. Darkness also affects communication. Visual signals between vehicles or between a vehicle and the surface are impossible. All communication relies on sound or delayed data transmission. This separation reinforces the autonomy of deep-sea vehicles. Once they descend, they operate largely on their own, guided by pre-programmed instructions and limited acoustic commands. Comparisons with space are often made, but the darkness of the trench is different. In space, stars provide distant points of light. Earth glows. The sun dominates. Even in shadow there is context. In the trench there is none. Darkness is complete not because light is absent everywhere, but because it cannot reach this far down. The weight of the ocean above absorbs it entirely. This absorption of light also means that energy from the surface does not penetrate easily. Photosynthesis is impossible. Life depends on chemical energy, detritus falling from above, or localized sources like hydrothermal vents. Darkness shapes the entire ecosystem, reinforcing scarcity and specialization. Understanding this requires observation under conditions that actively resist observation. The darkness of the Mariana Trench is not a dramatic void. It does not feel ominous in the way fiction often portrays darkness. It feels neutral, almost indifferent. It simply exists, unbroken and unchanged by human presence. Lights flare briefly, illuminate a patch of seafloor, then move on, leaving no trace. For exploration, this means that every mission is fragmentary. You do not see the trench as a whole, you see moments, isolated scenes, a rock face here, a patch of sediment there, a brief movement at the edge of the light. Stitching these moments into a coherent understanding takes years, and even then the picture remains incomplete. Darkness also enforces humility. It reminds us that visibility is not a given, that knowing a place requires more than reaching it. The trench does not reveal itself willingly. It does not offer sweeping vistas or clear boundaries. It offers only what you illuminate, and even then, only partially. As exploration continues, engineers and scientists develop better lights, more sensitive cameras, and improved image processing. But no technology can change the fundamental fact that the Mariana Trench exists in a state of permanent night. Light will always be imported, artificial, limited, and costly. This absolute blackness shapes everything else. It compounds the effects of pressure, cold, and distance. It turns navigation into calculation, observation into interpretation, and exploration into a series of careful guesses. And as we move forward, the darkness remains, not as a dramatic obstacle, but as a quiet condition that never lifts, reminding us that some places on Earth are not meant to be seen easily, or all at once. Cold is often imagined as something sharp, a sudden chill, a blast of winter air, the kind of cold that makes you pull your shoulders in and breathe more carefully. But the cold of the Mariana Trench is not sharp. It does not arrive suddenly, and it does not leave. It is slow, steady, and constant, woven into the environment so completely that it stops feeling like a condition and starts feeling like a rule. Down there, cold is not weather, it is structure. As water descends from the surface toward the trench, it gradually releases the heat it absorbed from the sun. By the time it reaches the deepest layers, that warmth is long gone. Temperatures near the bottom of the Mariana Trench hover just above freezing, typically between 1 and 4 degrees Celsius. This is not a seasonal average. It is not a winter low. It is the temperature, year after year, century after century, unchanged by surface cycles. This permanence is one of the most alien aspects of the trench. On land, seasons shape nearly everything. Temperature rises and falls, light lengthens and shortens. Ecosystems respond in rhythms that are predictable, even if they are sometimes harsh. In the trench, there are no seasons, no summers, no winters, no dawns or dusks. The environment exists in a state of near-perfect thermal monotony. For exploration, this constant cold presents challenges that are easy to underestimate. Cold affects materials. Metals contract, plastics become brittle, batteries lose efficiency, lubricants thicken. Electronics generate less heat, but also struggle to maintain stable operating conditions. Systems designed for surface temperatures must be insulated, heated, or otherwise protected to function reliably in near-freezing water for extended periods. But heating systems add complexity. They consume energy, introduce failure points, and require careful control. Too much heat can create thermal gradients that stress materials or interfere with sensors. Too little heat can lead to condensation, ice formation in certain components, or slow degradation of performance. Managing temperature becomes a balancing act, one that must function flawlessly without maintenance once a vehicle descends. Cold also affects time. Chemical reactions slow down. Biological processes operate at reduced rates. Mechanical wear behaves differently. Things last longer in some ways, but fail more quietly in others. A system might not break dramatically. It might simply stop responding as expected, its components moving just slowly enough to miss a critical window. For living organisms in the trench, cold is not a stressor. It is normal. Their metabolism is adapted to it. Growth is slow, movement is deliberate, energy is conserved carefully. This creates ecosystems that function on timescales very different from those at the surface. Events unfold slowly. Changes are subtle. Observing these processes requires patience that exploration missions rarely have the luxury to provide. Isolation compounds the effect of cold. The Mariana Trench is not just deep, it is distant. It lies far from continental shelves, far from shipping lanes, far from the infrastructure that supports frequent human activity. Reaching it requires long voyages across open ocean. Once there, ships must operate independently, carrying everything they need for weeks or months at a time. This isolation limits flexibility. If something breaks, replacement parts are not readily available. If weather turns unfavourable, schedules must adjust. If a mission fails, repeating it may take years. The trench does not allow casual experimentation. Every attempt is deliberate, carefully planned, and constrained by logistics. Isolation also means that the trench is largely unaffected by surface disturbances in the short term. Storms pass overhead without reaching the bottom. Waves dissipate long before they can influence conditions at depth. Even large-scale climate variations take time to propagate downward. The trench exists in a kind of environmental separation, buffered from the rapid changes that characterize the surface world. This separation contributes to the absence of seasons. Seasonal temperature changes are driven by variations in sunlight and atmospheric circulation. Neither of these reach the trench. The water down there was last in contact with the surface decades, centuries, or even longer ago. It carries the thermal signature of a distant past, slowly mixed and redistributed through global ocean circulation. From an exploration standpoint, this creates a paradox. On one hand, the stability of conditions simplifies planning. There is no need to account for seasonal storms at depth, no variation in light or temperature to consider once below. On the other hand, this stability removes opportunities. There are no optimal windows, no periods of increased visibility or biological activity triggered by seasonal change. Every moment is essentially the same. Cold and isolation also shape the chemical environment. The deep ocean is rich in certain dissolved gases and nutrients, but poor in others. Oxygen levels can be low, though not absent. Chemical gradients form slowly and persist for long periods. Hydrothermal vents, where they exist, create localized pockets of higher temperature and chemical activity, but these are rare and difficult to locate. Exploring these features requires precise navigation and extended observation, yet the cold limits how long instruments can operate. Power drains faster, mechanical systems degrade, sensors drift. The longer a vehicle remains at depth, the greater the chance that something will fail quietly rather than dramatically. For crewed missions, cold reinforces the sense of detachment from the surface world. Inside a submersible, temperature is controlled, but the awareness of the surrounding environment remains. Outside the hull, water just above freezing presses in from all sides. There is no warmth anywhere nearby, no variation, no refuge beyond the vessel itself. This knowledge affects decision-making. Risk tolerance decreases. Time on the bottom is carefully rationed. Every action is weighed against the cost of staying longer in an environment that offers no assistance and no forgiveness. Isolation also affects communication. Acoustic signals travel slowly and are subject to distortion. There is no continuous connection with the surface. Conversations are delayed. Data arrives in fragments. Decisions must often be made locally, without immediate input from support teams. This autonomy is necessary, but it increases pressure on both humans and machines. The absence of seasons also means that biological rhythms differ fundamentally from those at the surface. Many trench organisms do not experience cycles of abundance and scarcity driven by seasonal productivity. Instead, they rely on irregular inputs of organic material sinking from above, or on localized chemical energy sources. This unpredictability shapes behavior, reproduction, and survival strategies. Studying these rhythms requires long-term monitoring, something that remains extremely difficult at trench depths. Instruments left on the seafloor must survive pressure, cold, and corrosion for years. Retrieving them is a challenge in itself. Data transmission from fixed installations is limited. As a result, much of what we know is based on snapshots rather than continuous records. Cold also interacts with pressure in subtle ways. Material properties change differently when both factors are present. A component that performs well under pressure at moderate temperatures may fail under the combined stress of pressure and cold. Testing for these combined effects is complex and expensive, and not all scenarios can be simulated accurately in laboratories. Isolation further limits learning from failure. When something goes wrong in the trench, understanding exactly why can be difficult. Wreckage may be unrecoverable. Data logs may be incomplete. The environment does not provide clear feedback. Lessons are learned slowly, and progress advances in small increments. The world without seasons also affects our perception of time. On the surface, time is marked by change. Day follows night. Warmth follows cold. Growth follows dormancy. In the trench, time is marked mostly by accumulation. Sediment settles. Chemical reactions proceed. Organisms grow slowly. Changes happen, but they are not dramatic. For explorers, this creates a disconnect. Missions are short, intense bursts of activity inserted into an environment that operates on much longer timescales. The trench does not respond quickly to observation. It does not reveal patterns easily. Understanding it requires patience that exceeds the duration of most missions. Cold, isolation, and the absence of seasons combine to create an environment that feels static, but is not. It is active in ways that are subtle and slow. Processes unfold quietly. Energy moves gradually. Life persists without hurry. For humans accustomed to rapid feedback and visible change, this can be frustrating. Yet this very stillness is part of what makes the Mariana Trench so resistant to exploration. It does not meet us halfway. It does not adapt to our schedules or our expectations. It remains cold when we arrive and cold when we leave. It remains isolated regardless of our presence. It does not mark time in ways we recognize. As exploration continues, these conditions will remain constant challenges. Technology may improve, materials may become more resilient, power systems may last longer, but the trench will still be cold. It will still be isolated. It will still exist in a world without seasons, operating on its own terms. Understanding this helps explain why exploration has been so limited and why progress feels slow. The Mariana Trench is not a frontier that opens gradually with familiarity. It is a place that remains fundamentally separate, not because it is hidden, but because it exists under conditions that strip away many of the advantages humans rely on. And as we move forward, these conditions will intersect with another challenge, one that grows directly out of cold and isolation. The question of how or whether our machines can truly function where human bodies cannot, and what it means to explore a place almost entirely through tools that must survive where we never could. When humans cannot go somewhere safely, we send machines instead. This idea feels straightforward, almost reassuring. Machines do not breathe. They do not panic. They do not feel cold, fear, or isolation. In theory, they should be perfect explorers for places like the Mariana Trench, and yet the machines we send into the deepest ocean are not triumphant conquerors of an extreme environment. They are compromises, carefully engineered, tightly constrained, and constantly at risk. Their presence does not erase the difficulty of the trench. It translates that difficulty into mechanical terms. Every machine sent to the bottom of the Mariana Trench is designed around one central reality. It must survive conditions that would instantly destroy an unprotected human. This shapes everything. Size, shape, materials, power systems, sensors and control logic are all dictated by survival first and exploration second. There is no flexibility in that order. A machine that gathers excellent data but fails structurally is useless. A machine that survives but gathers limited data is considered a success. The most iconic of these machines are deep-sea submersibles, both crewed and uncrewed. Crewed submersibles are essentially pressure vessels with windows, propulsion, and life support systems attached. Their design philosophy is conservative by necessity. Thick walls, minimal openings, redundant systems. Every added feature increases risk. As a result, crewed vehicles that can reach extreme depths are rare, expensive, and limited in capability. Uncrewed vehicles, often called remotely operated vehicles or autonomous underwater vehicles, offer more flexibility. They do not need life support. They can be smaller. They can take more risks. But they are still constrained by pressure, cold, darkness, and isolation. Removing the human does not remove the environment. Pressure dictates the form of these machines. Most deep-sea vehicles rely on spherical or near-spherical pressure housings for sensitive components. Spheres distribute stress evenly. Flat surfaces do not. This means that electronics are often packed into small, dense cores, surrounded by thick shells. Space is limited. Heat dissipation is difficult. Maintenance is challenging. Propulsion systems must function in near-freezing water under immense pressure. Electric motors are sealed and pressure compensated. Hydraulic systems are carefully balanced. Moving parts are minimized because every joint is a potential failure point. Speed is sacrificed for reliability. Deep-sea vehicles move slowly, deliberately, conserving energy and reducing the risk of collision. Power is one of the most limiting factors. Batteries must operate reliably under pressure and cold. Traditional battery chemistries lose efficiency at low temperatures. Heating batteries consumes energy. Carrying more batteries adds weight, which must be countered with buoyancy. Some vehicles use lithium-based systems specially designed for deep-sea use, but even these have limits. Cables are another challenge. Tethered vehicles allow for real-time control and continuous power, but tethers long enough to reach the Mariana Trench would be heavy, fragile, and difficult to manage. They could snag on the trench walls or be damaged by currents. As a result, most trench-capable vehicles are untethered, relying on onboard power and autonomy. Autonomy, however, is imperfect. Programming a machine to handle unexpected conditions in a complex environment is difficult. Sensors may fail. Terrain may be different from expected. Sediment clouds may obscure vision. Acoustic navigation may drift. When a vehicle is untethered and thousands of meters below the surface, there is no quick way to intervene. The machine must decide how to respond, often with incomplete information. Communication with these machines is slow and limited. Acoustic signals carry commands and data, but bandwidth is low and latency is high. Sending a simple instruction can take seconds to reach the vehicle, and confirmation can take just as long to return. This makes fine control impossible. Operators must think ahead, issuing general instructions rather than precise commands. Sensors are the eyes and ears of these machines, but they are constrained by the environment. Cameras require light. Sonar provides shape but not texture. Chemical sensors must withstand pressure and remain calibrated. Each sensor adds complexity and power demand. Designers must choose carefully, knowing that they cannot bring everything. Robotic arms, often used to collect samples, are particularly challenging. They must operate precisely in darkness, under pressure, with limited feedback. Force sensors help prevent damage, but they add complexity. Touching the seafloor risks stirring sediment. Grasping objects risks crushing fragile samples. Every movement must be slow and deliberate. Even landing on the seafloor is risky. The bottom of the trench is not a flat, predictable surface. It can be soft, uneven, or sloped. A vehicle that lands improperly may tip, sink into sediment, or become unstable. Recovering from such situations autonomously is difficult, sometimes impossible. Recovery itself is another critical phase. Vehicles must return to the surface reliably. Buoyancy systems often rely on releasing ballast weights. These systems must function perfectly. If a ballast release fails, the vehicle may be lost permanently. Redundant systems are used, but redundancy adds weight and complexity. The loss of vehicles is not uncommon. Some are never recovered, others return damaged. Each loss represents not just financial cost, but lost data and lost learning opportunities. This risk makes institutions cautious. Missions are planned conservatively. Innovation proceeds slowly. The machines we send are also shaped by what we want to learn. Geological studies require different tools than biological surveys. Mapping requires different sensors than sampling. Because missions are rare, vehicles are often designed to perform multiple roles, which can dilute their effectiveness in any one task. There is also the issue of longevity. Ideally, we would place long-term monitoring stations in the trench, allowing continuous observation. In practice, maintaining such stations is extremely difficult. Power supplies run out, corrosion occurs, biofouling, even at depth, can interfere with sensors. Retrieving and servicing instruments requires new missions. Some experiments have involved dropping landers into the trench. These are simple platforms that descend, collect data, and then return. They are robust and relatively inexpensive compared to submersibles, but they are limited. They cannot move horizontally. They cannot adjust their position. They provide data from a single point. Advanced machines are being developed, but progress is incremental. New materials are tested. Better pressure-resistant electronics are designed. Improved batteries are researched. Each advance opens small new possibilities, but none eliminate the fundamental constraints. One of the most important limitations is that machines do not experience the environment. They record data, but they do not integrate it into understanding the way humans do. Human explorers notice patterns intuitively. They adjust their focus. They respond creatively. Machines follow instructions. Their observations are filtered through sensors and algorithms. This does not mean machine exploration is inferior. It means it is different. Understanding emerges later, on the surface, when scientists interpret data. This separation slows discovery. It also increases the chance of misinterpretation because context is limited. The trench magnifies this separation. Data arrives delayed, fragmented, and incomplete. A camera records a brief scene. A sensor logs a reading. Piecing these together into a coherent picture takes time and often raises new questions, rather than answering old ones. Despite these challenges, machines are our only viable explorers of the Mariana Trench. They extend our reach into an environment that will never be hospitable to human bodies. But they do not make the trench accessible in the way that vehicles make land or air accessible. They operate at the edge of feasibility. Every mission is an experiment not just in science, but in engineering. Will the hull hold? Will the batteries last? Will the navigation system remain accurate? Will the vehicle return? Success is measured not in comfort or completeness, but in survival and partial insight. The machines we send carry our curiosity downward, but they also carry our limitations. They are shaped by what we can build, what we can afford, and what we are willing to risk. They do not conquer the trench. They visit it briefly, cautiously, and then retreat. As technology advances, these machines will improve. They will become more reliable, more capable, more autonomous. But the trench will still impose its rules. Pressure will still crush. Darkness will still obscure. Cold will still sap energy. Isolation will still separate machine from maker. And as we move forward, another question begins to surface. If machines are the only way we can explore the trench, what happens when the environment itself begins to favour life over machinery, revealing a world where adaptation, not engineering, has already solved problems we still struggle to understand? At first glance, it seems unfair. We build machines out of hardened steel, advanced composites, and carefully engineered systems, and they struggle to survive in the Mariana Trench. Meanwhile, fish, crustaceans, and microorganisms move through that same environment as if it were ordinary. They do not implode, they do not malfunction. They eat, reproduce, and continue their lives under pressures that crush our most sophisticated technology. The contrast invites a simple question, but the answer is anything but simple. The reason submarines struggle where fish thrive is not because our engineering is crude. It is because biology and machinery solve problems in fundamentally different ways. Submarines, whether crude or robotic, are designed to preserve an internal environment that resembles the surface. Even uncrewed vehicles protect sensitive components by isolating them from the surrounding pressure. They rely on rigid structures to keep the outside out. Fish and other deep-sea organisms do the opposite. They do not resist pressure, they live within it. This difference begins at the most basic level. A submarine must maintain a pressure differential. Inside, pressure is kept relatively low to protect electronics, batteries, and structural integrity. Outside, pressure increases relentlessly with depth. The hull exists to hold that difference in place. Every meter deeper increases the stress on that barrier. Every hour adds fatigue. The deeper the dive, the more the entire mission depends on the flawless performance of a single physical boundary. Fish have no such boundary. Their bodies are already in equilibrium with the surrounding pressure. They contain no large air-filled cavities that need protection. Their tissues are mostly water, and water does not compress easily. This means that as pressure increases, their bodies simply adjust without structural failure. There is no dramatic moment where the environment becomes hostile. Pressure is just part of the background. This difference extends down to the cellular level. The proteins that make up biological tissues in deep-sea organisms are adapted to function under extreme pressure. Pressure can alter the shape of proteins, affecting how they fold and interact. In surface organisms, this would disrupt essential processes. In trench organisms, molecular structures are stabilized in ways that preserve function. Enzymes continue to work. Cell membranes remain flexible. Metabolism proceeds slowly but reliably. Machines, by contrast, are assembled from materials that were never meant to operate under constant compression. Even when pressure-resistant alloys are used, they are fighting the environment rather than cooperating with it. Seals must remain tight. Housings must remain intact. Every interface between components becomes a vulnerability. Another key difference lies in energy use. Submarines and deep-sea vehicles rely on stored energy. Batteries must power propulsion, sensors, lighting, communication, and onboard processing. Energy is finite. Once it runs out, the mission ends. In contrast, trench organisms operate on extremely low energy budgets. They do not move quickly. They do not waste motion. Many spend long periods nearly motionless, conserving resources. Food in the trench is scarce. There is no photosynthesis. Energy arrives slowly, either as organic matter sinking from above or as chemical energy from localized sources. Life has adapted to this scarcity by becoming efficient. Growth is slow, reproduction is infrequent, nothing is wasted. This efficiency is not something machines can easily replicate. A vehicle consumes energy simply by existing, by keeping systems ready, by maintaining stability. Buoyancy illustrates another contrast. Submarines must carefully manage buoyancy to control depth. Ballast systems add or release weight. Buoyant materials are compressed under pressure, reducing their effectiveness. Maintaining neutral buoyancy becomes increasingly difficult as depth increases. Fish, on the other hand, have bodies whose density is naturally matched to the surrounding water. Some deep-sea species lack swim bladders entirely, avoiding the complications of gas-filled spaces under pressure. Their buoyancy is passive, stable, and effortless. Movement also differs fundamentally. Submarines push against water using propellers or thrusters. This requires power and generates turbulence. Fish move by flexing their bodies and fins, transferring energy efficiently into forward motion. Their movements are subtle, optimized over millions of years to minimize energy loss. They can hover, turn, and adjust position with remarkable precision, all without complex machinery. Sensory systems provide another point of divergence. Submarines rely on instruments, cameras, sonar, pressure sensors, chemical detectors. These systems must be powered, calibrated, and interpreted. They provide data, but often without context. Fish rely on senses integrated directly into their bodies. Many deep-sea species detect vibrations, pressure changes, and chemical cues with extraordinary sensitivity. Some can sense minute movements in water that no mechanical sensor could detect without amplification. Vision, where it exists, is specialized. In the deep ocean, eyes are adapted to low light or bioluminescence. Some species can detect wavelengths invisible to humans. Others rely less on vision and more on touch and chemical sensing. These sensory strategies are flexible and resilient. They do not depend on external power sources or fragile components. Reproduction highlights another mismatch. Machines are built to last a certain number of missions. Components wear out. Maintenance is required. Failure is inevitable. Biological organisms reproduce, passing on adaptations that improve survival. Over time, populations adjust to subtle environmental pressures. There is no equivalent process for machines. Each new design must be created deliberately, tested, and deployed. Evolution happens slowly in engineering terms. The environment itself favors biological solutions. The trench is stable in temperature, pressure, and chemistry over long timescales. This stability allows life to adapt precisely to local conditions. Machines, by contrast, are often designed for versatility. They're expected to function in multiple environments, from testing facilities to deployment sites. This generality makes them less optimized for any single extreme. There is also the matter of repair. When a machine fails in the trench, it cannot fix itself. A cracked housing or a failed circuit means the end of the mission. Biological organisms constantly repair themselves. Cells regenerate. Damage is isolated and healed. Even under extreme conditions, life maintains itself through continuous maintenance at the microscopic level. Isolation further amplifies these differences. Submarines operate alone. There is no support network at depth, no spare parts, no assistance. Organisms exist within ecosystems. Sparse though they may be, these ecosystems provide interactions that support survival. Scavengers recycle nutrients. Microbes break down organic matter. Energy flows slowly but persistently through networks of life. Another important distinction is time. Machines are designed for relatively short operational periods, hours, days, occasionally weeks. Life in the trench operates on geological timescales. Species have persisted there for millions of years. Their adaptations are not responses to single events, but to persistent conditions. What seems extreme to us is simply normal to them. This difference in timescale affects resilience. A machine must be perfect from the moment it arrives. A small flaw can end everything. A biological organism can survive imperfections. It can adjust behavior. It can endure damage. Survival does not require flawless performance, only sufficient adaptation. The struggle of submarines is also shaped by human expectations. We want machines to gather large amounts of data quickly. We want high-resolution images, precise measurements, and comprehensive coverage. These demands increase complexity. Complexity increases vulnerability. Fish have no such goals. They do not need to map the trench or transmit data. They only need to survive. Even the presence of a submarine can disrupt the environment in ways that do not affect fish. Lights attract or repel organisms. Noise travels far in water. Pressure waves from movement can alter local conditions. Fish are part of this environment. Submarines are intrusions. This does not mean that engineering is failing. It means that engineering is attempting something fundamentally different from what biology has already solved. Submarines are temporary visitors. Fish are permanent residents. The trench rewards permanence, efficiency, and integration. It punishes intrusion, excess, and resistance. Understanding this contrast helps explain why exploration remains so limited. We are trying to observe a world using tools that are not native to it. We build barriers between ourselves and the environment, then struggle to maintain those barriers under constant stress. Life removes the barrier entirely. This realization has influenced recent research. Instead of trying to overpower the environment, some engineers study biological adaptations for inspiration. Flexible materials, pressure-tolerant electronics, energy-efficient movement. These ideas hold promise, but translating them into reliable machines is difficult. The trench remains a place where life has succeeded quietly and persistently, while machines arrive briefly and cautiously. Submarines do not fail because they are poorly made. They struggle because they are outsiders in a world that favours those who belong to it. As exploration continues, this tension will remain. Machines will improve, but they will never thrive in the way life does. They will always be guests tolerated briefly by an environment that has no need for them. And this raises a deeper question, not about engineering, but about what it truly means to explore a place where survival itself requires a way of being we cannot adopt. To call life in the Mariana Trench strange is not an insult. It is an acknowledgement that it operates according to rules that feel incompatible with everything we know from the surface world. This is life without sunlight, without seasons, under crushing pressure, near freezing temperatures and chronic energy scarcity. And yet, it exists. Not barely, not temporarily, but persistently. It grows, feeds, reproduces and adapts in an environment that seems designed to prevent exactly those things. The difficulty in understanding trench life begins with a simple mismatch in expectations. On the surface, life is shaped by abundance and variation. Energy arrives daily from the sun. Ecosystems pulse with cycles of growth and decay. Movement is relatively easy. In the trench, none of that applies. There is no photosynthesis, no day-night rhythm, no warmth arriving from above. Life does not respond to abundance, it responds to limitation. Most of the energy that sustains life in the trench originates far above it. Organic material produced near the surface slowly drifts downward as dead plankton, fecal pellets, and fragments of larger organisms. By the time this material reaches Hadal depths, it has been consumed, decomposed, and diluted many times over. What arrives is sparse, irregular, and nutritionally depleted. This slow rain of particles is sometimes called marine snow, but at trench depths it is more like dust. Some areas receive occasional larger inputs. A dead whale sinking to the seafloor becomes a temporary oasis, supporting a burst of activity that may last decades. Landslides can deliver organic rich sediment. But these events are unpredictable and rare. Most of the time life persists on very little. Because energy is scarce, trench organisms are adapted for efficiency. Growth rates are slow, lifespans are often long. Reproduction may involve fewer offspring with higher chances of survival. Nothing is wasted. Movement is deliberate. Many species spend long periods nearly motionless, conserving energy in an environment where unnecessary activity carries a cost. Pressure, which destroys unprotected human bodies and machines, is simply part of the background for trench life. The bodies of these organisms contain no large air-filled spaces. Their tissues are largely incompressible. But the real adaptation happens at the molecular level. Proteins, enzymes, and cell membranes are structured to function under pressure that would denature surface-dwelling equivalents. High pressure alters the way molecules interact. It can force proteins to unfold or change shape, disrupting their function. Trench organisms counter this with biochemical strategies that stabilize these structures. Some produce specialized molecules that protect proteins from pressure-induced deformation. Others adjust the composition of their cell membranes to maintain flexibility and integrity. Temperature compounds these challenges. Near-freezing conditions slow chemical reactions. Metabolism proceeds at a reduced pace. This is not a temporary slowdown, it is the normal state. Trench organisms are not waiting for warmer conditions. Their entire biology is tuned to cold stability. The absence of light shapes life in profound ways. Vision, where it exists, is highly specialized. Some organisms have reduced or absent eyes, relying instead on touch, vibration, and chemical sensing. Others have eyes adapted to detect faint bioluminescent flashes produced by nearby organisms. These flashes may be used for communication, attraction, or camouflage. Bioluminescence is one of the few sources of light in the deep ocean, but even this is rare in the deepest trench regions compared to shallower zones. Energy is too precious to spend freely on light production. When it occurs, it is brief and purposeful. A signal, not a glow. Many trench organisms are small. Gigantism, which appears in some deep-sea environments, is less common at the greatest depths. Scarcity favours compact bodies that require less energy to maintain. Soft tissues are common. Hard shells are less so, though some crustaceans and mollusks do exist. Their structures adapted to resist pressure without relying on internal voids. Among the most well-known trench inhabitants are amphipods, small shrimp-like crustaceans that scavenge organic material. Some species have been found at depths exceeding 10,000 meters. Their bodies are flexible, their exoskeletons adapted to pressure, their metabolism efficient. They play a key role in recycling nutrients, breaking down organic matter that would otherwise accumulate. Fish do exist at Hadal depths, though they are rare and specialized. Species such as the Mariana snailfish have been observed near the bottom of the trench. These fish lack swim bladders, which would be problematic under pressure. Their bodies are gelatinous, reducing density differences with surrounding water. Their bones are less mineralized, which helps prevent brittleness. At the microbial level, life is even more abundant. Bacteria and archaea thrive in sediments and water, driving chemical processes that sustain the ecosystem. Some microbes use chemosynthesis, deriving energy from chemical reactions rather than sunlight. In areas near hydrothermal activity, these processes can form the base of localized food webs. Microbial life also plays a role in breaking down organic material that sinks from above. This recycling is slow but persistent. Over long timescales, it shapes the chemistry of the trench environment. Understanding these processes requires sampling and observation that are difficult to achieve without disturbing the system. One of the challenges in studying trench life is that it often does not survive the journey to the surface. As pressure decreases during ascent, cellular structures fail. Gases dissolved under pressure come out of solution. Tissues rupture. What arrives at the surface may bear little resemblance to how the organism functioned at depth. This creates a bias in our understanding. We tend to know more about organisms that can tolerate pressure changes or that are observed in situ via cameras. Many species may exist that we have never seen clearly, simply because our methods of observation are insufficient. Even when organisms are observed, interpretation is difficult. Behavior captured on camera may not reflect normal activity. Lights may alter behavior, noise may cause stress responses, the presence of a vehicle may change local conditions. Every observation is influenced by the act of observation itself. The trench ecosystem is also shaped by isolation. Populations are often small and separated by large distances. Gene flow may be limited. This can lead to high levels of specialization and endemism. Species found in one trench may not exist elsewhere. This makes the Mariana Trench not just deep but biologically distinct. Evolution in such environments proceeds slowly. Stable conditions reduce selective pressure for rapid change. Adaptations that work tend to persist. This stability can make trench life seem ancient, even if individual species are not especially old. The environment itself changes slowly, and life reflects that pace. From a human perspective, this kind of life challenges assumptions about habitability. Conditions we label as extreme or impossible turn out to be perfectly viable for organisms adapted to them. This has implications beyond Earth. Studying trench life informs discussions about potential life on other planets or moons with subsurface oceans, but exploration remains constrained. Each mission provides limited glimpses, a few hours of video, a handful of samples, a snapshot of a system that operates continuously, slowly, and largely unseen. We piece together understanding from fragments, aware that much remains unknown. The strangeness of trench life is not just in its appearance or adaptations, it is in its quiet persistence. Life does not announce itself there. It does not flourish in bursts. It endures. It fits itself precisely into narrow constraints and remains there, unaffected by human curiosity. This endurance is part of why the trench remains elusive. It is not empty, but it is not accommodating. Life exists on its own terms, indifferent to observation. Machines arrive briefly, lights flicker on, data is collected, and then the environment returns to its steady state. As we move forward, this raises difficult questions. How much of trench life remains undiscovered not because it is rare, but because it does not intersect easily with our methods? How many adaptations remain unseen because they operate at scales or timescales we struggle to measure? The Mariana Trench reminds us that life does not need comfort, variety, or abundance. It needs compatibility. And in that deep, dark, cold, pressurized world, life has found compatibility in ways that still challenge our understanding. And this brings us to another limitation, one that sits between our machines and the life they attempt to observe. Even when we can reach the trench, even when life is present and active, staying long enough to truly understand it remains one of the hardest problems of all. Reaching the bottom of the Mariana Trench is often described as an achievement, and in many ways it is. But reaching a place and being able to stay there are very different things. In the history of exploration, the difference between a brief visit and sustained presence has always mattered. Crossing a mountain pass once is not the same as living in the mountains. Touching down on a remote island is not the same as understanding its ecology. In the trench, this difference becomes extreme. We can arrive, but we cannot remain. And that limitation shapes everything we know. Every descent to the trench is governed by time, not in the abstract sense, but in a very practical one. How long can the vehicle survive? How long will the power last? How long before pressure, cold, or mechanical fatigue introduce unacceptable risk? These questions dominate mission planning long before scientific goals are discussed. The result is that trench exploration is built around short windows of opportunity, measured in hours rather than days. The craft that make these descents possible are, by necessity, fragile in a very specific way. They are not weak, they are carefully balanced. Their strength lies in precision rather than excess. A deep-sea vehicle capable of reaching the trench is engineered to tolerate exactly the stresses it will face, with very little margin beyond that. Adding more material indiscriminately does not prove safety. It increases weight, complicates buoyancy, and introduces new failure points. This fragility is not always visible. From the outside, a submersible may appear solid, almost overbuilt. Thick walls, reinforced joints, heavy components, but under trench conditions, every material is closer to its limits than it would ever be on land. The craft is not leisurely resisting pressure. It is holding back a force that is constantly trying to close it inward. Because of this, extended stays become risky. Time under pressure is not neutral. Materials experience fatigue. Seals are stressed continuously. Electronics operate under conditions that accelerate degradation. Even if nothing dramatic happens, the probability of failure increases with every passing hour. This creates a practical ceiling on how long missions can safely last. Power systems reinforce this limit. Batteries are finite, and at depth, they are working under unfavourable conditions. Cold reduces efficiency. Pressure affects housing integrity. Every system draws power simply to remain operational. Lights, cameras, sensors, computers, propulsion, thermal control all consume energy continuously. There is no idle state where consumption drops to zero. This means that time spent at the bottom must be rationed carefully. Descent takes hours, ascent takes hours. What remains is a narrow window for observation. Every minute is weighed. Do you move to a new location, spending power on propulsion? Do you stay still and collect longer observations? Do you use brighter lights for clearer images, or dim them to conserve energy? These are not abstract choices. They determine what data is collected and what remains unseen. The fragility of craft also limits experimentation. On land or in shallow water, equipment can be tested, adjusted, repaired, and redeployed quickly. In the trench, testing happens in real conditions with no second chances. If a new instrument fails, the mission may still succeed, but that instrument is lost. If a new design introduces an unforeseen interaction, it may compromise the entire vehicle. This encourages conservatism. Proven designs are favoured over experimental ones. Incremental improvements are preferred to radical changes. While this approach increases safety, it slows progress. Exploration advances in careful steps, each one building cautiously on the last. Another aspect of fragility is recovery. A vehicle that reaches the bottom must return. There is no infrastructure at depth, no docking stations, no repair platforms. Ascent typically relies on releasing ballast, allowing buoyancy to carry the craft upward. This system must work flawlessly. If ballast does not release, ascent may be impossible. Redundant release mechanisms are used, but redundancy adds complexity. More components mean more potential failure points. Each added safeguard must itself be safeguarded. The system becomes a network of dependencies, all of which must function correctly in an environment where repair is impossible. Staying down longer also increases the risk of becoming stuck. The seafloor of the trench is not a flat, solid surface. It can be soft, uneven, and unstable. Vehicles can sink into sediment or settle at awkward angles. Even a small tilt can complicate ascent or interfere with ballast release. The longer a vehicle remains stationary, the greater the chance that sediment will shift around it. Environmental disturbances add uncertainty. While the trench is generally calm, it is not static. Small-scale sediment movements occur. Chemical gradients shift. Seismic activity, though infrequent, can happen without warning. A tremor that would be barely noticeable on land can trigger sediment slides along the steep walls of the trench. These factors make long-term habitation unthinkable with current technology. Even deploying fixed installations is difficult. Instruments placed on the seafloor must survive pressure, cold, corrosion, and potential burial by sediment. Power supplies must last for years or rely on energy harvesting methods that are still experimental at such depths. Retrieving long-term instruments is its own challenge. Finding them again requires precise navigation. Acoustic beacons help, but they can fail. Sediment can cover markers. The seafloor may shift. A retrieval mission may find nothing where an instrument was expected to be. Because of these difficulties, much of our understanding of the trench comes from brief snapshots. A few hours of video, a small number of samples, a set of sensor readings taken during a single descent. These snapshots are valuable, but they are incomplete. They capture moments, not processes. Processes are what scientists often want most. How does sediment accumulate over time? How do biological communities change? How do chemical conditions fluctuate? These questions require sustained observation. Without the ability to stay down there, answers remain tentative. The inability to stay also affects interpretation. When you only see a place briefly, it is easy to mistake coincidence for pattern. An organism observed once may seem rare when it is simply elusive. A geological feature may appear static when it is slowly changing. Without repeated observation, context is missing. Human presence amplifies these issues. Crewed missions are especially constrained. Life support systems limit duration. Psychological stress increases with time in a confined, isolated environment. Decision-making becomes more cautious as fatigue sets in. For safety reasons, crewed stays at the bottom have been extremely short. Uncrewed missions offer more flexibility, but they are still bound by power and reliability. Autonomous systems can extend duration somewhat, but they introduce new uncertainties. Software must handle unexpected situations. Sensors must operate without oversight. Errors may go unnoticed until it is too late. There is also the matter of cost. Every hour spent at depth increases the expense of a mission. Ships, crews, equipment, and support systems all operate on tight budgets. Funding agencies and institutions must weigh the value of longer stays against the increased risk and cost. Often, the safer choice is shorter missions with clearer endpoints. This economic reality further limits ambition. Exploration becomes selective. Only certain questions are pursued. Only certain locations are visited. The trench remains vast and mostly unobserved, not because of a lack of interest, but because of practical constraints. The problem of staying down there is not just technical, it is conceptual. Our exploration models are based on environments where presence can be sustained. Camps can be established. Bases can be built. Infrastructure can grow. The trench does not allow this progression. It does not support gradual settlement or expansion. Instead, exploration resembles deep space probes rather than terrestrial expeditions. Brief encounters, limited interaction, long periods of analysis afterward. Knowledge accumulates slowly, mediated by machines that must return intact. This creates a sense of distance that persists even after a successful mission. The trench does not feel closer because it has been visited. It remains remote, defined by the fact that we cannot linger. Our understanding advances, but our relationship to the place does not fundamentally change. Staying matters because familiarity changes perception. When humans can remain in an environment, They notice details, patterns, and anomalies that brief visits miss. They develop intuition. They learn what is normal. In the trench, we lack this familiarity. Everything remains novel, even after decades of study. As technology advances, efforts continue to extend mission duration. Better batteries, more efficient systems, improved materials. Each improvement stretches the window slightly, but the fundamental problem remains. Pressure, cold, isolation, and fragility combine to enforce limits that cannot be easily overcome. The Mariana Trench allows entry, but it does not allow residence. It tolerates brief visits, but it resists occupation. And this resistance is not dramatic or hostile. It is quiet, structural, and persistent. Understanding this helps explain why, despite decades of effort, the trench remains one of the least explored places on Earth. We have been there. We know it exists. We have seen parts of it. But we have not stayed long enough to make it familiar. And this limitation leads directly to another challenge. Even when we do manage to reach the bottom, even when our machines survive and return, communicating with that distant world and transmitting what they experience back to us introduces yet another layer of separation, one that further complicates exploration. Communication is something we usually take for granted. Messages move instantly. Voices travel without effort. Images appear on screens the moment they are captured. Even when communication fails, it usually fails temporarily. A dropped signal, a delayed message, something that can be fixed by moving a few steps or waiting a few seconds. At the bottom of the Mariana Trench, communication does not fail in that familiar way. It becomes fundamentally constrained, reshaped by the environment into something slower, narrower, and far less reliable. The problem begins with a simple physical fact. Radio waves, which carry most modern communication, do not travel well through water. Seawater absorbs electromagnetic signals efficiently, and the deeper you go, the worse the problem becomes. By the time you reach even moderate depths, radio communication is effectively impossible. At trench depths, it is not an option at all. This single limitation forces deep-sea exploration to rely on a completely different method of communication. Sound is the primary alternative. Acoustic signals can travel long distances through water, far better than radio waves. Whales communicate this way. Submarines navigate this way. Deep-sea vehicles depend on it almost entirely. But sound comes with its own constraints, and those constraints become more severe the deeper you go. Acoustic communication is slow. Sound travels through water at roughly 1,500 meters per second, which sounds fast until you consider the distances involved. A signal sent from the surface to the bottom of the Mariana Trench must travel nearly 11 kilometers downward. The reply must travel back up. This introduces delays measured in seconds, not milliseconds. For human conversation or real-time control, this delay is significant. Bandwidth is another issue. Acoustic signals cannot carry large amounts of data efficiently. High-resolution video streams, detailed sensor arrays, and complex telemetry quickly overwhelm available bandwidth. As a result, vehicles must prioritize what information they send. Much of the data they collect is stored on board and only reviewed after the vehicle returns to the surface. This delay and limitation fundamentally change how exploration works. Operators cannot see what the vehicle sees in real time. They receive fragments, status updates, low-resolution previews. Decisions must be made without full information. By the time a command reaches the vehicle, conditions may have changed. By the time a response returns, the moment has passed. In shallow water, tethers can solve some of these problems. A cable provides power and high bandwidth communication. But at trench depths, tethers become impractical. A cable long enough to reach the bottom would be heavy, fragile, and difficult to manage. It would be subject to tension, abrasion, and entanglement along the trench walls. Deploying and retrieving such a tether safely is beyond current capabilities for routine missions. This means that most trench-capable vehicles are untethered. Once they descend, they are effectively on their own. Communication becomes intermittent. Commands are sent sparingly. Autonomy becomes essential, not because it is ideal, but because there is no alternative. Autonomy introduces its own challenges. A vehicle must interpret sensor data, maintain stability, avoid hazards, and execute mission objectives without continuous guidance. Software must anticipate a wide range of scenarios, many of which are difficult to test in advance. Unexpected terrain, sediment clouds, or sensor failures can confuse algorithms designed under controlled assumptions. When communication is limited, errors are harder to correct. If a vehicle misinterprets its environment, operators may not realize it until much later. By then, opportunities to intervene may have passed. In extreme cases, a vehicle may be lost without a clear understanding of what went wrong. Sound itself behaves unpredictably in the deep ocean. Temperature, pressure, and salinity affect how sound waves travel. These factors create layers that bend, reflect, or scatter acoustic signals. In a trench, with its steep walls and complex geometry, sound can behave erratically. Echoes overlap, signals weaken or distort. Interference increases. This makes acoustic positioning difficult. Vehicles rely on networks of acoustic beacons to determine their location. At extreme depths, maintaining accurate positioning requires careful calibration and constant adjustment. Small errors accumulate. Over time, a vehicle's estimated position may drift significantly from its actual location. Communication barriers also affect safety. In surface exploration, emergencies can be communicated instantly. Help can be requested. Decisions can be coordinated. In the trench, emergencies unfold in isolation. A critical failure may occur without immediate awareness at the surface. By the time operators receive warning signals, options may be limited. For crewed missions, this isolation is especially stark. A human inside a submersible cannot simply speak to a support team. Messages must be sent acoustically, delayed and compressed. Conversation becomes sparse and deliberate. This affects decision-making and increases psychological pressure. Even routine communication carries weight. Every message sent uses energy. Every transmission risks interference. Vehicles must decide when to speak and when to remain silent. Silence is not unusual. Long periods may pass with little or no contact as the vehicle carries out pre-planned tasks. This separation changes how scientists engage with exploration. On land, researchers adjust their focus dynamically, responding to what they see. In the trench, planning happens in advance. Objectives are defined before descent. Adjustments are limited. Discovery becomes something that happens later during data analysis, rather than in the moment. The barrier is not just technical, it is interpretive. Data sent from the trench arrives stripped of context. A sensor reading without visual confirmation, an image without spatial orientation, a sound recording without clear source identification. Interpreting these fragments requires caution and often raises more questions than answers. Communication barriers also limit collaboration. In many scientific endeavours, multiple teams work together, sharing observations in real time. In trench exploration, collaboration is delayed. Data is shared after missions conclude. Feedback loops are slow. Hypotheses are tested over years rather than days. The idea of placing permanent communication relays at depth has been explored, but this introduces new challenges. Such systems would require long-term power sources, maintenance strategies, and protection from pressure and corrosion. Retrieving or repairing them would require additional missions, each with its own risks. Some experiments have used acoustic modems and relay systems to improve communication, but gains are incremental. The fundamental limitations remain. Sound is slower and less flexible than electromagnetic communication. Water absorbs and distorts signals. Depth magnifies every difficulty. There is also the issue of noise. The ocean is not silent. Natural sounds from geological activity, distant storms, and biological sources create a constant background. Human activity adds more noise. Distinguishing meaningful signals from this background becomes harder at depth, where signal strength is limited. All of this contributes to a sense of separation that persists even after a mission succeeds. When a vehicle returns with data, that data represents a past experience. The moment is gone. There is no opportunity to ask follow-up questions in real time. Understanding unfolds slowly, reconstructed from recordings and logs. This temporal separation matters. It affects how knowledge is built. Insights emerge gradually. Misinterpretations may persist until corrected by later missions. The trench remains something we learn about after the fact, not something we engage with directly. Communication barriers also reinforce the feeling that the Mariana Trench exists beyond our immediate reach, not just physically, but informationally. Even when we touch it, we cannot talk to it easily. We cannot listen continuously. We receive echoes, not conversations. As technology advances, some of these barriers may soften. Better acoustic systems, smarter autonomy, improved data compression. Each improvement helps, but none remove the fundamental constraint imposed by water and depth. The bottom of the planet remains a place where communication is slow, uncertain, and fragile. Messages arrive late. Details are lost. Context must be inferred. Exploration becomes an exercise in patience and interpretation. And beyond communication lies another challenge, perhaps the most unsettling one of all. Even if we could communicate perfectly, even if machines could stay indefinitely and report everything they observe, the trench still holds the possibility that much of what lies there has not yet intersected with our instruments at all, remaining unseen not because we fail to look, but because we do not yet know how to look. When we say that the Mariana Trench is largely unexplored, it is tempting to imagine hidden creatures, dramatic landscapes, or singular discoveries waiting patiently in the dark. That image is appealing, but it's also incomplete. What the trench might still be hiding from us is not just a list of unknown objects or species, it is entire processes, relationships, and patterns that remain invisible because our ways of observing are brief, indirect, and constrained by the very environment we're trying to understand. The most obvious unknown is biological. Every descent into the trench has revealed life where we once assumed there might be very little. Amphipods, snailfish, microbes, and other organisms have been documented at depths once thought uninhabitable. But these observations are sparse. They represent moments, not surveys. It is entirely possible and even likely that many species remain undiscovered simply because they do not intersect with our cameras or sampling tools during the short windows we are present. Life in the trench may also exist in forms that do not fit our expectations of what an organism looks like. Much of biology has been built around surface-dwelling life, with its reliance on sunlight, oxygen-rich environments, and relatively moderate conditions. Trench life may rely on biochemical pathways that are rare or absent elsewhere. Microbial communities in particular may play roles we do not yet understand, driving chemical cycles that sustain larger organisms in subtle ways. There is also the question of distribution. We tend to think of the trench as a single environment, but it is not uniform. Conditions vary along its length and depth. Chemical composition, sediment type, and geological activity differ from place to place. Life may be highly localized, forming pockets of activity separated by vast stretches of relative emptiness. Without comprehensive mapping and repeated observation, these patterns remain hidden. Beyond biology, geology holds many unanswered questions. The trench is an active tectonic feature. The Pacific Plate continues to slide beneath the Mariana Plate, generating earthquakes, deforming rock and reshaping the seafloor. Much of this activity occurs slowly, but not all of it. Small-scale movements, sediment slumps and fault adjustments happen without warning. These processes influence the shape of the trench and the habitats available to life, yet we observe them only indirectly. Our maps of the trench floor are incomplete. Sonar provides outlines, but resolution decreases with depth and distance. Fine-scale features such as fractures, vents, or small formations may go undetected. Even when features are identified, their nature may be unclear without direct observation. A mound might be sediment, rock, or biological in origin. Distinguishing between these requires context we often lack. Chemical processes are another hidden layer. The deep ocean is chemically dynamic, though changes occur slowly. Gradients of oxygen, carbon, nitrogen, and other elements shape biological activity. Hydrothermal systems, where they exist, introduce heat and chemicals from within the Earth, creating localized environments very different from the surrounding cold sea floor. Some of these systems may be too subtle or too small to detect with current instruments. The trench also interacts with the broader ocean in ways we are only beginning to understand. Deep currents move water masses slowly but persistently. These currents transport heat, nutrients, and dissolved gases. They connect the trench to distant parts of the planet, linking it to global climate systems on long timescales. Small changes in these deep currents could have consequences that ripple upward, but observing them requires long-term data that we do not yet have. Another possibility is that the trench hides records of Earth's past. Sediment accumulating at the bottom of the trench settles slowly, layer by layer. Over time, these layers may preserve chemical signatures, microfossils, or other markers of past conditions at the surface. In this sense, the trench floor could function as an archive, storing information about climate, biological productivity, and geological events over millions of years. Accessing and interpreting this archive is technically challenging and still in its early stages. There is also the matter of scale. Some phenomena may be too small or too slow to notice during brief visits. Microbial interactions, gradual chemical diffusion, and long-term biological succession do not announce themselves dramatically. They require sustained observation to become visible. Without the ability to remain in the trench for extended periods, these processes remain largely inferred rather than observed. Human impact adds another layer of uncertainty. Even the deepest parts of the ocean are no longer completely isolated from surface activity. Microplastics have been found in trench sediments. Persistent pollutants can sink and accumulate. The long-term effects of these materials on trench ecosystems are unknown. It is possible that changes are already underway that we have not yet documented. The trench may also be hiding limits, not just discoveries. There may be boundaries to life, pressure thresholds beyond which complex organisms cannot function, or chemical conditions that restrict diversity. Understanding where these limits lie is just as important as finding new species. It informs our understanding of habitability, both on Earth and elsewhere. Another unknown is how representative the Mariana Trench is of other deep trenches. There are several Hadal zones around the world, each with its own geological and chemical context. Are the patterns we observe in the Mariana Trench unique, or do they reflect broader principles? Without comparative studies, it is difficult to say. The trench might be hiding general rules about life under extreme pressure, or it might be an outlier shaped by local conditions. Technological limitations also hide information by filtering what we can detect. Instruments are designed with certain targets in mind. Cameras capture what is illuminated. Sensors measure what they are built to measure. Anything outside those parameters remains invisible. This creates blind spots that we may not even be aware of. There may be phenomena occurring that we have not imagined, and therefore have not designed tools to observe. Even when data is collected, interpretation can obscure as much as it reveals. A pattern seen once may be overemphasized. A rare event may be mistaken for a common one. Without repeated observation, it is hard to separate noise from signal. The trench does not provide easy feedback to correct our assumptions. There is also the possibility that the trench hides nothing dramatic at all, at least by human standards. It may be largely as we have seen it: sparse, quiet, stable, and slow. If so, that itself is a meaningful finding. It would tell us something about the limits of complexity under extreme conditions, and about the kinds of environments that persist without constant change. But even that conclusion would need to be supported by far more data than we currently possess. Absence of evidence is not evidence of absence, especially in a place we visit so rarely and for such short periods. What the trench might still be hiding from us is therefore not just unknown life or unexplored terrain, but uncertainty itself. It hides the fact that our understanding is provisional, shaped by limited access and constrained methods. It hides processes that unfold too slowly or too subtly for brief observation. It hides context that would only emerge through sustained presence. This hiddenness is not accidental. It is a direct consequence of the trench's conditions. Pressure limits duration, darkness limits perception, isolation limits communication, fragility limits experimentation. All of these factors work together to keep much of the trench beyond our immediate grasp. As technology advances, some of these barriers may weaken. Longer-lasting instruments may be deployed. Better sensors may reveal finer details. Autonomous systems may operate for extended periods. Each step forward will reduce the amount the trench hides from us, but it is unlikely that it will ever be fully revealed. The Mariana Trench does not yield its secrets easily, not because it is hostile, but because it is indifferent. It does not change to accommodate observation. It does not respond to curiosity. It simply continues to exist under conditions that strip away many of our usual advantages, and this leads naturally to the final question. If the trench remains so resistant to exploration, if it continues to hide more than it reveals, what does that say about our relationship with frontiers in general, and about why some places on Earth may remain beyond reach, not temporarily, but by their very nature? There is a tendency, especially in an age shaped by rapid technological progress, to assume that every barrier is temporary, that every limit is simply a challenge waiting for the right invention, the right funding, the right moment. History seems to support this belief. We learn to cross oceans, to fly, to reach space, to send machines beyond our solar system. From that perspective, the Mariana Trench can feel less like a boundary and more like an unfinished task, something incomplete rather than unreachable. But frontiers are not all the same, and some resist not because we lack ingenuity, but because the conditions that define them actively undermine the ways we explore. The Mariana Trench is not beyond reach in the absolute sense. We know where it is. We know how deep it goes. We have touched its floor. We have recorded images, collected samples, and confirmed the presence of life. But reach is not a single moment of contact. Reach implies continuity, access, and familiarity. It implies the ability to return easily, to stay, to adjust plans, to learn through repetition. By that standard, the trench remains beyond reach, not dramatically, but persistently. One reason some frontiers resist us is that they are not empty spaces waiting to be filled by human presence. They are environments with their own stable states, shaped by forces that do not align with human needs or technological convenience. The trench does not lack activity. It lacks compatibility. Pressure, darkness, cold, and isolation are not obstacles that can be removed without fundamentally changing the environment itself. They are the environment. This distinction matters because many past frontiers became accessible precisely because humans could eventually adapt themselves to the conditions. Clothing, shelter, agriculture, and infrastructure allowed people to live in deserts, polar regions, and high mountains. Even spaceflight works by creating controlled environments that can be sustained for extended periods. In the trench, the cost of sustaining such an environment grows rapidly with depth, while the benefits remain limited. Another factor is that the trench does not reward presence in obvious ways. Frontiers that attract sustained exploration often offer resources, strategic advantage, or immediate scientific payoff. The deep ocean offers insight, but not abundance. It does not provide materials that are easy to extract or environments that support large-scale human activity. Its value lies primarily in knowledge, and that knowledge arrives slowly. This slows momentum. Without the ability to scale up exploration, each mission remains isolated. There is no gradual build-up of infrastructure, no path toward routine access. Every expedition begins almost from scratch, constrained by the same limitations as the last. Progress becomes incremental rather than transformative. There is also a mismatch between the pace of the trench and the pace of human systems. Funding cycles, academic careers, and technological development timelines operate on years or decades. The trench operates on geological and biological timescales. Many of the processes scientists hope to understand unfold too slowly to be captured by short missions. This creates frustration and uncertainty. Results are partial. Conclusions remain tentative. Frontiers also remain beyond reach when observation itself alters what is being observed. In the trench, light, sound, and physical disturbance all change local conditions. The very act of exploration becomes an intrusion. This complicates interpretation and limits how much confidence we can place in what we see. It becomes harder to separate natural behavior from response to disturbance. Another reason some frontiers resist exploration is that they expose the limits of our tools rather than the limits of our courage. There is no shortage of willingness to descend into the trench. What is lacking is a way to do so repeatedly, safely, and informatively. The tools we rely on are optimized for environments where pressure is low, light is available, and communication is fast. Adapting them to the trench requires trade-offs that reduce their effectiveness. It is also worth considering that not all frontiers are meant to be crossed quickly. Some serve as reminders rather than destinations. The Mariana Trench reminds us that Earth is not fully mapped or mastered even now, that large portions of our own planet remain unfamiliar, not because we ignored them, but because they exist under conditions that resist our presence. This reminder has value. It tempers assumptions about control and access. It challenges the idea that technological capability automatically translates into understanding. It encourages humility in the face of environments that do not respond to ambition alone. There is a tendency to frame frontiers as problems to be solved, but some frontiers function more like boundaries that define perspective. The trench defines the lower extreme of Earth's habitable environment. It shows how life adapts when energy is scarce, pressure is immense, and change is slow. It expands our understanding not by becoming familiar, but by remaining different. The phrase, "for now," matters here. It acknowledges that technology evolves, that methods improve, that future generations may find ways to observe the trench more effectively. Longer-lasting instruments may be deployed, autonomous systems may operate for years, new materials may reduce fragility. Each of these advances could shift the boundary slightly. But even with these advances, the trench is unlikely to become accessible in the way other frontiers have. It will not host permanent human presence. It will not support large-scale infrastructure. It will remain a place we visit indirectly, through machines and data rather than one we inhabit. This does not make exploration futile. It makes it selective. It forces us to ask better questions, to value quality of observation over quantity of access, to accept that some knowledge arrives slowly, through accumulation rather than immersion. There's also something important in recognizing limits before they are fully overcome. It allows us to choose restraint, to decide that not every place needs to be entered frequently or extensively, that some environments may be better understood at a distance, through careful, minimal interaction. The Mariana Trench also invites comparison with other frontiers, both terrestrial and conceptual. Deep space, the interior of planets, the origins of life, the nature of consciousness. These are areas where progress is real but bounded, where understanding grows without familiarity. The trench belongs in this category. It is not a stepping stone, it is a reference point. Frontiers that remain beyond reach serve another function as well. They preserve uncertainty. In a world increasingly mapped and measured, uncertainty becomes rare. The trench resists closure. It leaves room for questions that cannot yet be answered fully. This uncertainty drives inquiry without promising resolution. As exploration continues, our relationship with the trench may change, but its role likely will not. It will remain a place where human presence is temporary, mediated, and limited, where knowledge is partial and provisional, where the environment sets the terms, and that may be enough. Not every frontier needs to be conquered to be meaningful. Some are valuable precisely because they remain just beyond comfortable reach, reminding us that the world is larger, deeper, and more complex than our systems can fully capture. The Mariana Trench exists quietly under kilometers of water, unchanged by our attention. We will continue to visit it briefly. We will continue to learn from it slowly. And it will continue to resist familiarity, not as a challenge issued to us, but as a condition of its existence. For now, that resistance is not a failure of exploration. It is part of what defines the place itself,